just wait on the
Yeah.
people side. Okay, I think we can get started. Good morning, everyone. Today's speaker is Andrew Chael, an associate scholar at the Princeton Gravity Initiative. He earned his PhD in physics from Harvard University in 2019 under the supervision of Ramesh Narayan, and went on to hold a NASA Hubble Einstein Fellowship at the Princeton Center for Theoretical Science. Andrew is a key member of the Event Horizon Telescope collaboration, and he has made significant contributions to our understanding of accretion, relativistic jets, and polarization imaging of black holes, with his expertise in computational and analytical tools. Okay, take it away.
Yeah, thank you so much for having me. It's really great to be back in this room and talking a little bit about what I've done since I graduated from here, now 6 years ago, which is crazy. So yeah, I'm going to talk today about just a general set of what we know about polarized black hole images, what we've learned from studying these things at the horizon scale and polarization over the last 5 years, roughly. And in particular, what I think we're beginning to learn about the connection between polarized images and black hole spin and black hole energy extraction, which has sort of been the driving thing in my research for the last couple of years now. So just as background, I think this beautiful panel of images is put together by Sarah Isaun, who's here, and it just shows an array of black hole jets throughout the universe. So these extragalactic jets were discovered about 100 years ago, first in the galaxy M87, which is our most well-studied jet, but then of course we see them all over in radio, and they deliver energy and momentum out from the centers of galaxies to extragalactic distances, and along with other types of outflows play a key role, we think, in regulating galactic evolution. In M87, the jet that I think was first discovered more than 100 years ago and is the best studied, that we see this beautiful jet in optical in the HST image. And then once the advent of radio astronomy and interferometry, we're able to look at it in radio light, see that it's delivering this huge lobes of material past the outside of the galaxy, and then track it inward closer and closer to the center, the central object that launches the jet with very long baseline interferometry, connecting radio telescopes around the world. And when I was a PhD student, this was the highest resolution image we had of this jet, put out in 2018. And we thought that at the very center of this image was the supermassive black hole that actually launches the jet. And so the big question that motivated some of the early work with the Event Horizon Telescope is, what does this jet launching look like on event horizon scales? And of course, I don't need to tell this audience, I think, at this institute about the EHT, but it's a collection of radio telescopes operating millimeter wavelengths, connected all over the world by very long baseline interferometry, and just doing the simple calculation of the frequency or the wavelength of light we're looking at, 1.3 millimeters, which is the highest frequency VLBI ever been performed. Well, now I guess we're up to 0.8 millimeters, but at the time. And the diameter of the Earth, effectively the diameter of our Earth-sized telescope, by connecting these different telescopes together, we get 20 microarcseconds, which is an extreme resolution, just exactly what we need to resolve the image of the central massive black hole on scales of the event horizon. And so we produced this image right at the end of my PhD in 2019. And since then, we've been studying it in more and more detail, and particularly adding polarization to try to learn more about the magnetic fields around this black hole. So yeah, we have this supermassive black hole at the heart of M87. We think it's surrounded by a hot sub-Eddington accretion flow with temperatures exceeding 10 to the 10 Kelvin. It launches this powerful relativistic jets to huge distances. We still have a lot of questions about it, and many of them are things that I think about in my work. But in particular, today I want to talk a little bit about how we can learn more about how these jets are launched from images at this very small scale. And do these images tell us things about the spin of the black hole and the strength of geometry of the magnetic field? But I also think about things like tests of gravity and plasma physics around the black hole. So if you have questions about those, please let me know. So the key ingredient to really, I think, get insights of the astrophysics and physics of the black hole out of these images is polarization. And why is that? It's because synchrotron radiation that we observe from supermassive black holes is emitted with its polarization perpendicular to magnetic field lines, which are threading the event horizon and doing all sorts of crazy stuff in the environment around the black hole. And so just in a naive case, you could imagine just taking the direction of polarization that we observe and rotating it 90 degrees to learn something about the geometry of the magnetic field. It turns out things are much more complicated in this environment. We have things like the light bending from general relativity. We have aberration from special relativity. We have Faraday rotation, changing the direction of the polarization we observe. But all these complicating processes are also sensitive to interesting things we care about in the space-time, like the space-time, like the properties of the plasma. And so all together, even though it's a complicated problem, these polarization images are really diagnostic of what's going on close to the event horizon, and both the astrophysics side and the plasma that's accreting and being launched in jets, and the space-time itself. So we found just by studying these polarization images over the past 5 years that there's an incredible amount you can learn about both astrophysics and physics with these polarized images of black holes. So in this talk, I'm going to talk a little bit first about just an overview of what we learned from comparing polarized images of black holes with simulations. This might be a review for many of you because it's like recapping what sort of the EHT collaboration has done, but I think it's important to set the stage. Then I'll talk a little bit about my own work, about what polarized images tell us about jet launching, and then hopefully at the end I'll have time to talk a little bit about what's next and the work I'm currently doing and what I think we can hopefully learn from future observations with things like the next generation EHT and the Black Hole Explorer. So yes, please interrupt me throughout the talk if you have questions. I'm really happy to discuss as we go along. And yeah, we'll just get started. So first, what have we learned from this sort of campaign that we've undergone with the EHT to compare polarized images of M87 to simulations? So this was work that was done in a series of papers led by the EHT collaboration, some of which I led as a coordinator. So this is the only slide I have here on sort of the imaging process in the EHT. This is a big part of my research, is actually trying to, on the data side, trying to understand how we can get the best possible images out of the EHT data, which is very complicated and corrupt and has all sorts of systematics we have to deal with. And this slide just shows that one of the ways that we approach this hard problem is by throwing many independent methods at it and doing these campaigns to try to compare results across methods. And this slide is showing that all the methods in the case of the first polarized image of M87 show very consistent structure, where we see a ring of emission around 50 microarc seconds, around 5 times the gravitational radius on the sky. And we see a consistent ring diameter between all these images. We see a consistent sense of asymmetry, where it's brighter on the south. And in polarization, which is in these ticks, indicating the direction of polarization and the color indicating the level of fractional polarization in the image, we see that the polarization is predominantly helical, so the ticks are sort of in this right-handed helix, if you consider the axis through into the plane of the page. And the polarization level is weak, around 10%. So yeah, I spent a lot of time thinking about how we can get the best possible images. This is just one slide to show that we think about this a lot, but I'm really happy to answer questions on that if you have them. Of course, just last week, we sort of upgraded that set of images for the first time in a while. So this was work that was led by Paul Tita here at CFA to take the image that we had in 2017 and expand it to future years of observations. So we looked at, as a collaboration, the image in 2018 and 2021 observations. And we found very consistent behavior in sort of the overall shape of the ring over 4,000 gravitational timescales over these 4 years. But the polarization seems to be changing in interesting ways, in that the polarization structure is shifting a little bit, and the fractional polarization actually seems to be much lower in 2018 and 2021. And this is something I think we're still trying to understand physically and connect our simulations to learn more about. I'll talk a little bit about it at lunch, but yeah, I think this is a big open question, is what exactly is going on and to cause these changes from year to year. Yes?
Are the ticks to the same scale in all the 3 panels?
Yes, that's right. Yeah, it's all on this one scale here. Yeah.
I don't see a factor of 3 change between 2017 and 21.
Yeah, I think that's a good point. I think like if you were to look at tick by tick, it seems like the change is probably less. This factor of 3 is sort of in the average diagnostic that we use, this M average, which I agree can be confusing. Yeah, so exactly how to characterize the level of polarization, I think, is an important question in dealing with these comparisons, for sure. Okay, so how do we take these images that we observe from the EHT and try to learn things about the environment, the astrophysical environment around the black hole? The sort of best tools we've had to do this is this combination of general relativistic magnetohydrodynamic simulations, which are these complicated supercomputer simulations which have solved the coupled equations of plasma dynamics and a magnetic field in the curved spacetime around a black hole. And one of the real successes of these simulations is that they sort of self-consistently predict how material accretes and then launches these jets, which we observe at large scales, from extracting the spin energy of the black hole. And then we take these simulations and we put them through this ray tracing pipeline where we track light rays as they're bent around the black hole, as they go through all of this magnetized plasma, and solve for the radiation that is accumulated along those rays and which we would observe as a distant observer. And so this GR radio transfer codes take these simulations to produce movies like this, which show the sort of turbulent evolving plasma around the black hole, as well as the polarization structure, which is dancing here in these ticks. Then what we do is we take very large libraries of these simulations, which cover a large range of parameters, covering things like the black hole spin, the structure of the magnetic field. In particular, a big uncertainty we have is what is going on with the electron temperature. And so we have to parameterize because these simulations don't actually predict the temperature of the electrons, we have to parameterize it after the fact. This is what I'm going to talk about again a little bit at lunch. And so we cover a different range of temperature models. We produce this large library of simulations. Here you can see them both at sort of the native resolution of the simulation, and then what we would observe with the EHT blurred to the resolution of our instrument, covering a range of these different simulations. So one of the key variables in these simulations is the magnetic field structure. So we sort of have two classes of simulations in these large libraries, which we sort of call this sane-mad dichotomy. And in the magnetically arrested case, or the MAD case, we have very strong coherent magnetic fields which build up on the horizon. This is a slice through an average simulation, and you can see that in this case the fields are they're very ordered. They build up on the horizon. They launch these jets very effectively. And then we also have the sane case, or the standard and normal evolution case, where magnetic fields are weak and turbulent. These are dependent on the initial condition, but you can see in this case that instead of having fields which are building up on the black hole coherently and pushing back and sort of determining the motion of the plasma, in this case the fields are sheared along with the plasma is sort of telling them what to do, and they get all tangled up. And they still launch jets, but they are much, much weaker. And that's because the jets in these simulations are launched by this Blandford-Znajek process, where magnetic fields that build up on the horizon of the black hole here extract the spin energy of the black hole in order to launch the jets. And the power of these jets is proportional to the magnetic flux squared times the spin squared. And so even before we did all this work, this sort of MAD paradigm was a very appealing way to sort of explain how we could get very powerful jets like an M87, because if you can sort of maximize the amount of magnetic field you're putting onto the black hole, you can get more power out of it and produce stronger jets. So one thing I just wanted to emphasize, and I try to emphasize this more in talks these days, is that these EHT images are actually very consistent with this picture we were getting from GRMHT simulations. And this, I don't think, had to happen. I think it's not, wasn't a priori that the simulations we were running and like using various approximations and initial conditions, which who knows how well motivated they are, would produce things that looked as similar to the actual images that we observe. And so I think the fact that just immediately the first images we observed of black holes actually do look like our simulations blurred once we blur them with the resolution of the EHT is telling us that we're getting at least something about the overall state of the plasma in these simulations correct about what's going on in the black hole. Yeah, the level of variability, I think, is a key question. So in Sag star, for example, we have seen that the simulations are more variable than what we actually observe. So that, I think, is a key difficulty, but I think it's something that a lot of people are working on. Hopefully we can make progress on. But yeah, at least in the average, and I would say the simulations do predict variability, so it's not, the characteristic is not exactly what we observe. Yeah. Yes, so before polarization, when I was finishing up here, before we had started to look at the polarization of M87, we actually were in a situation where the simulation sort of predicted the image, or matched the images too well, and that like most simulation models could fit the total intensity observations, could fit this overall ring structure, as long as we tweaked the various free parameters we had, like the total mass of the black hole, which adjusts the size, or the position angle on the sky. We learned that the sort of overall image asymmetry, this overall north-south difference in the image, tells you that the black hole spin vector is facing away from Earth. So that was a constraint we could get. But overall, many different models with different electron temperatures, with different magnetic field topologies could fit the data. And so the question immediately became, can we do better with polarization? And I think we had high hopes that you could. And just by looking at this sample of images from simulations, I think you can see immediately why. Here in these images, again, the underlying grayscale is the total intensity, and the ticks are the polarization. These are just 4 different simulation images, and you can see that even though they have quite similar overall ring structures, they have very different structures in polarization, with strongly or weakly polarized emission and ticks that are radial or azimuthal or helical. And so just by looking at this, you could immediately see that the polarization could be more diagnostic of what's going on. And so what we did, once we turned to actually interpreting the polarized images that we observed, is to break down the images into these different metrics. So the unresolved and resolved polarization fractions, which tell us something about the polarization that we're seeing overall integrated over the entire source, or the polarization sort of averaged at the scale of the EHT resolution. And then a key variable that was introduced by Daniel Palumbo, who is a postdoc here, is this beta 2 parameter, which is the sort of characterizing the azimuthal structure. It's essentially the second Fourier mode of the image. So you take a sort of Fourier transform around the ring and look at the second mode. And this complex number tells you effectively what the sort of overall character of the polarization spiral is. So if you have beta 2 that's real, or equivalently you have an argument of beta 2 that's 0, you have radial polarization. If you have beta 2 that's -1, you have sort of this azimuthal polarization, and then different values in between, as you go to imaginary, give you left or right-handed spirals. And so this turned out to be really the key parameter in this overall simulation scoring, and we use it a lot to this day. So by comparing all these parameters from the images to the data, we were able to show in 2017 that that comparing the observations to our entire set of images really strongly favored a magnetically arrested accretion flow. So this is just one way we did this comparison, but it's sort of the simplest by just looking at the total number of passing images. And this is all of the simulations in the weak field limit, and this is all the magnetically arrested simulations. And you can just see that there's many more magnetically arrested simulations that pass all these constraints that we put on them from the real observations here. And we did this scoring in different ways, and they all give the same overall picture. This sort of dramatic narrowing of the space of simulations really allows us to constrain M87's allowed accretion rate, reducing it from sort of 3 orders of magnitude uncertainty to only 1. They give us estimates for sort of the overall character of the plasma, which are very consistent with analytic estimates we made in the same paper. Again, this sort of preference for overall magnetically arrested models I think, was really good news, in that these models really more easily launch Blandford-Znajek jets, and so they're more natural to explain what we observe at large scales in the jet in M87. But I think now we do have a question that to do these new EHT polarization measurements that we're observing from later years of observations actually change this picture. We haven't done this full pipeline of scoring yet, so that I think will come hopefully relatively soon, and so I encourage you to stay tuned for that. Yeah, I'm gonna skip this. I just mentioned that another thing we've done is look at Sag star in linear polarization as well. This is work that was also led here by Sarah Isoun and Angela Ricarte. And the polarization overall polarization image we observe in Sag star is actually very similar, with very similar sort of overall spiral of polarization overlaying the image of the black hole. We observe higher polarization fractions, so an average of like 25% instead of 10% or less than what we observe in M87. And this overall sense of the polarization spiral is actually consistent with sort of the clockwise sense of rotation, which is measured in near-infrared flares, but also now in millimeter flares as well from light curves from ALMA. Interestingly, the same sort of simulation scoring approach for Sag star prefers magnetically arrested simulations as well, but we don't seem to see a jet from Sag star at all. So it's I think, a really interesting question. And can these mad systems actually produce jets that we don't observe? Or why don't we see a jet if the overall state of the magnetic field is similar? OK, so that was just sort of an overview of where we stood in the overall EHT comparison of simulations to images. Now I'm going to talk a little bit about my own work and what we've learned over the past couple of years about what these polarization images tell us physically about energy flow and jet launching, and particularly in the case of M87, close to the black hole. So just to get its motivation, we know that this image that we observe with the EHT on horizon scales is just part of a much larger system where we observe this jet. This is a simultaneous observation campaign of the jet in M87 that was done at the same time as EHT observations, showing the jet at many different scales, at many different wavelengths, optical, X-ray, millimeter, gamma ray. And this sort of large-scale jet comes out of the very central region close to the black hole and delivers energy or momentum to vast scales. And we think that these jets are powered by this sort of BZ process, extracting energy from the black hole. But this isn't something we've ever actually observed directly or constrained at the scales we are looking at probing now with the EHT. And so I think a big goal that we have as a collaboration or as a field is to try to understand, can we actually directly observe energy extraction from black holes with these new types of images we're getting? Can we actually conclusively demonstrate that this is what is launching these jets, or is it some other process? Is it energy being extracted at larger scales from an accretion disk, for example? And I think in the simulation field, we have pretty strong confidence that that the energy from the jets is actually coming from the supermassive black hole, because that's what we observe in simulations. So when I was a grad student here, I did a set of simulations of the jet in M87, which are shown here at different wavelengths. And these simulations produce images of the jets which look a lot like what we actually observe. They produce the jet power in the measured range. They produce sort of a similar trend of opening angle with frequency and the same sort of core shift. And going back a long time, back to the early 2000s, these simulations, people have been able to go look in these simulations and see that the energy that is in these jets is directly being taken out from the central black hole, that this Blandford-Znajek process is actually what is producing the electromagnetic outflow.
So are these radiative GR emissions?
These ones happen to be radiative, yeah, but you see this in non-radiative as well, and as radiative, yeah. Okay, so simulations really nicely show that you're getting energy extraction from the black hole. This is a recent example from a paper led by Ramesh that I was on in 2022, showing that the trend of the jet efficiency with the black hole spin is exactly what you would predict from the Blandford-Znajek mechanism. And so in simulations, we think we are observing this BZ process at work. We think the simulations do a pretty good job of explaining what the jets actually look like. So it seems natural to assume that these jets are actually launched by extracting the spin energy of the black hole. But again, we aren't actually, that statement doesn't tell us, it doesn't provide us a direct test that just to say, like, we're looking at something directly in the image of the black hole. Can it tell us that energy is being extracted? And so that's what we started to try to pull apart by looking at these polarized images. So the polarized images of M87, again, here's an example. And here's this sort of breakdown of the polarization pattern in this beta-2 statistic. And again, this beta-2 parameter was the most constraining image feature. It's the one that's sort of most keyed in on magnetically arrested models when we looked at all the simulations and compared them to data. And so I started thinking a couple years ago, is there a way that we can actually interpret this beta-2 parameter physically? Is there something that we can, rather than just treating it as some parameter we compare to simulations, is there something we can learn about it, maybe by stepping back and looking at more simple models? And so we stepped back and looked at like the most simple possible model imaginable, which is instead of a full supercomputer simulation of black hole accretion, we look at this incredibly simple cartoon where we just are looking directly face on at a black hole, or not even a black hole because here we're in flat space. You can imagine there's a black hole there, but it's not doing anything. And we're looking at magnetic fields with different structure. So here the magnetic field lines are in blue. We have a toroidal magnetic field here. And we just flip the polarization 90 degrees. We ignore all the important effects from parallel transport through the space-time, through Faraday rotation, all these things that are actually, we think, quite important, but just try to build some intuition with this simple model. And so again, yeah, the polarization is 90 degrees to the magnetic field in all these cases, and you can see that if we just consider these different beta modes, if we measure a beta 2 of 0, an angle of beta 2, or a phase angle of beta 2 of 0 in this in this simple model, that would correspond to magnetic fields which are toroidal. A beta 2 of plus or minus 180 degrees, plus or minus pi, corresponds to radial magnetic fields. And then sort of intermediate values, either positive or negative values of this phase of beta 2, correspond to spirals which are either left or right-handed in the polarization. So a left-handed polarization spiral, again, with the axis going into the page, would correspond to a positive value of this phase of beta 2, and a right-handed polarization spiral would correspond to a negative value. And this is what we actually observed, this case in M87, or at least in 2017. Yeah?
How can we tell that it's only coming from the jet component? Like, will it be polluted by this component?
Yeah, that's a really good question. So again, this is just like a simple cartoon. Like, we're not considering disk or jet components or anything. But I think definitely as we start to extend this to like more realistic models, to more realistic analytic models, or just full simulations, we really do have to start to worry about where the emission is coming from. We think by looking at, in MAD simulations, the EHT emission is coming from mostly in the midplane. So it's kind of like a disk component. But yeah, at different frequencies, you could have emission from different regions, and there could also be other sorts of electron models which give us different emission as well. Yeah. Okay. So the thing we realized after staring at these and looking at the math for a long time is that actually a really interesting, sort of striking result from just these simple models is that this sort of right-handed polarization spiral corresponds to a overall a ratio of the phi component of the magnetic field to the radial component of the magnetic field that is less than 0. Again, that's just what you get directly from this cartoon picture by taking these polarization vectors and rotating them 90 degrees to get the sense of the field. And it turns out that if you just look at what the pointing flux in GRMHD is, in axisymmetric GRMHD, I should say, the pointing flux that you get, or the energy outflow in the electromagnetic field, is directly equal to the product of the radial and toroidal magnetic fields times -1 and a bunch of other stuff, including the angular speed of the fields. So if you think you know the direction that the fields are rotating, which we think we do in M87, we think that the overall direction of the angular momentum is into the plane of the sky from the overall asymmetry of the image. If you think you know that and can sort of fix the directions of your coordinate axis, this is saying that in the simple model, where we can just sort of directly infer this ratio of b phi over br from looking at beta 2, that tells us directly that we're observing energy that is outflowing out from the center of this image. Again, this is based on a lot of assumptions. We have to assume that we know the direction of the field line angular speed. We have to assume that we have this strong connection between beta 2 and the ratio b phi over br. But I think it was really striking that we made this connection and gave us some hope that this beta 2 is actually telling us something about the direction of energy flow around the black hole. So that's what this slide is saying. We then sort of had to immediately turn to more complicated models of M87 to see if this sort of overall connection between the beta 2 phase we measure, this negative beta 2 phase, and this overall field geometry, or this overall direction of energy flow from the central black hole held up. So we did that again by turning to GRMHD simulations. We looked at this large set of simulated images from Ramesh's simulations. These are all magnetically arrested simulations. And what we found is once we fixed, again, the direction of the spin of the black hole to be into the plane of the sky, that almost all of these simulation images had a negative value of this phase of beta 2, which is consistent with the energy outflow, which we know is happening in the simulation. So we can look at the simulation and say, is there energy outflow? In magnetically arrested simulations, there always is. Maybe when the spin is 0, a little less, but when you get higher spin, you get much more efficient outflows from the Blandford-Znajek process. And what we observed is that all of the observed beta 2 is consistent with this overall sign of being less than 0, corresponding to this sense, this direct connection between energy outflow and the observed polarization spiral that we made in just the simple models. Another fact that you can see just immediately by looking at these histograms is that this phase of beta 2 has a dependence on spin. So if we just look at the prograde simulations, as you increase the black hole spin, you go from a phase of beta 2 closer to -180 for the low spinning simulations to closer and closer to 0. That's essentially saying that your polarization pattern is becoming more and more radial as you increase the black hole spin. And this is the same qualitative dependence that we see in sort of simple models, which I skipped, but we also looked at simple models, sort of analytic models of BZ monopoles, which show the exact same dependence.
Does the blue band show observations?
Yeah, here the blue band shows observations from 2017, yeah.
That would suggest the spin.
Yes, so if you just take this one variable, and I'll talk about this a little bit in a few slides, you would infer from the 2017 EHT observations that you are either preferring low spin or maybe retrograde moderate spin. So the retrogrades have a similar dependence on spin, whereas you get more radial as you go to higher black hole spin value. But sort of the overall, all the distributions are squished more toward the left here. And we interpret that as happening because you're having some interference from the fact that at large distances, the disk is counter-rotating. So in the region where we're observing the EHT emission, everything is being frame dragged and pulled along with the black hole, but it's moving less rapidly in the retrograde case because it started out with an opposite sense of angular momentum farther away. Yeah. And that's exactly what I'm showing here, is that basically, even in the retrograde case here on the left, you can see the fields are co-rotating with the black hole once we get inside some critical region around 5 RG where the EHT is observing. And this is showing the field and angular speed transitioning from barely red here, so retrograde to prograde here in blue. And here's the sort of overall ratio of B phi over BR, which is transitioning from positive to negative as you go from further out from the large-scale disk to where the EHT emission is actually happening at around 5 RG. OK. So I showed in the last slide there's this connection to spin. This goes through a little bit more detail. So basically, in these simple models, right, we have that as you start with, if you start with initially radial fields, those are wound up by the black hole spin, and that's what produces the electromagnetic outflow that that is observed in the Blandford-Znajek mechanism, which we see in these simulations. But a low spinning black hole will spin up these fields less efficiently than a high spinning black hole. These are actual images of what a BZ monopole solution looks like. But they always wind it up in the same sense, so that this B phi over BR is less than 0. Basically, the fields are dragging behind the black hole. Yes, but how rapidly they do that depends on spin. This sort of increased field winding with spin increases the overall power of the Blandford-Znajek jet, or outflow you see, but it also makes the polarization we observe with the EHT more radial. So these are actual simulations, time averaged, which correspond to some models which we think are good fits to EHT data potentially, or at least they're magnetically arrested. And you can see in this low spinning case, spin of 0.1, you see a much more azimuthal polarization pattern corresponding to fields which are more radial. And in the high spinning case, you see a much more radial field corresponding to much more radial polarization pattern corresponding to fields which are much more wound up already at these scales. So yeah, exactly as you mentioned, we can also then just start to make some bold comparisons of what we actually observe with the EHT. This is the 2017 results to what the distributions are that we get from different simulations of magnetically arrested accretion. And so this is showing for this full range of simulations from Ramesh's M87 set, covering a bunch of different electron heating models, what the distribution of the phase of beta 2 is at each value of black hole spin. And you can see that you get this overall trend, again, whereas you go from 0, the polarization becomes more radial. You would say, just by comparing this one value, that we actually are preferring either quite low black hole spin or more potentially retrograde black hole spin, that there's a larger range of retrograde models which are consistent. And this is actually something that's been seen both in the original sort of EHT simulation comparisons, but then also several more recent works which have applied things like different machine learning methods or other different scoring approaches, or even in this case of this paper by Dominic Chang recently, who's a grad student here, looking at an analytic model. He also found a preference for retrograde spin. So I think this is really intriguing that many people are now sort of arriving at this result, which you can sort of just read off potentially if you boldly make this connection. And again, the overall sign difference, the fact that we're observing a negative arg beta 2 here, is consistent with the energy outflow, assuming we know the direction of the spin of the black hole is into the plane of the sky. Of course, this situation becomes more mysterious and confusing if we consider the recent results that just came out last week. So I'd have a much easier time giving this talk last week, but oh well. Because in 2021, we actually observed a change in sign, or a shift about 60 degrees in the overall sense of this arg beta 2 parameter. So this band in 2021 is the one up here. And you can see that's still consistent with some of the low spinning retrograde models, but it's unclear if those are favored. We haven't done the full sort of comparison of simulations to observations yet for the 2021 results that we've done for the 2017 results. So yes, so hopefully that will come soon. But I think this does raise a question, are we actually seeing sort of a low spinning retrograde model as you would naively read off here? Are we seeing some kind of change in the magnetic field which isn't captured in our simulations? Or are we seeing potentially a change in the external Faraday screen where if maybe some material far away from the black hole is causing Faraday rotation that affects the overall sense of the polarization pattern we observe? Maybe there's some material in the jet in between us and the black hole image, for example, that is changing over time and causing this. But I think we need to really dig into all these possibilities, and we're doing that now. So hopefully next time I give this talk, I can give a better answer on this. Yeah?
That little big retrograde spin.
Yeah.
Are you saying the black hole reverse spin, or what is it?
Oh, what I'm saying there is, if you just look here, right, like low spinning retrograde, so here the minus 0.3, I would say is still consistent, right? Because these minus 0.3, minus 0.5, you're still getting some emission sort of from the boundary layer where the material is reversing. And so you actually get some models where you have the opposite sign of beta 2.
You had already concluded retrograde from the previous image.
Yeah, I would say
you're saying it may still be okay.
Yeah, but I would say retrogrades may still be okay, but it would, I think, push you down toward the lower spinning retrograde, and then I think you start to get worried if the jet power is sufficient. So, yeah. I think it's, if you just take it at face value and you ignore Faraday rotation, you're really starting to narrow the space of models you would be allowed, and probably really focusing in on this low spinning retrograde, and that might be concerning if you're worried about jet power, yeah. Okay, so this is the same plot now for Sagittarius star. For Sagittarius star, we have a wider range of uncertainty, at least for now, on what the sort of derotated, because Sagittarius star has more significant Faraday rotation, but we're able to take it out, on what the range of beta 2 values is. So you can see it's consistent with many more models. But I think what is interesting is that this sort of overall, for Sagittarius star, we don't have a good sense of what the spin direction is just from the image alone, like we did from M87. But if you sort of assume there's energy outflow in Sagittarius star and then sort of reverse the argument and try to use this value to infer the direction of black hole spin, you would say, again, just like M87, Sagittarius star spin is pointing into the plane of the sky, and therefore things are rotating clockwise on the sky. And that sort of inference from this polarization is actually consistent with what is observed with near-infrared flares, which are tracked by the gravity interferometer and by sort of modeling of ALMA millimeter light curves, which is done by Maciek-Wilgus with simple hotspot models. All of these seem to rotate clockwise. And so this sort of consistency of the overall polarization spiral with that clockwise sense of rotation, I think, is intriguing. So all this is to say that these polarimetric spin measurements, I think, are possible, and I think they will get better as we start to understand this relationship and its systematics and its uncertainties more and more. And yeah, I think that this is not something we even knew about a few years ago, and hopefully in the next few years, as we really start to dive into the models and try to pin down these uncertainties, I think we might be in a place where we can really start to make precise measurements of black hole spin from polarization. And then I think the exciting thing would be to really see if we can try to make similar, or lower quality, but similar measurements of other sources which are less well resolved and apply this technique there. Okay, so good. In the last part of the talk, I'm going to talk a little bit about sort of next steps, what we're hoping to apply, these sort of insights from simulations and analytic models, and learning about the connection between spin and polarization to future observations. And I think the sort of big class, again, I don't have to talk here about this too much, but the big sort of classes of future observations which we're hoping to achieve are sort of divided into two classes. So first is sort of zooming out with sort of the next generation Event Horizon Telescope or extensions to the EHT, sort of enhancing our dynamic range and making more direct connections between the horizon scale structure, which we're observing with the EHT now, and the extended jet. And the other is to sort of zoom close in and to get really high resolution images with the Black Hole Explorer, which would be extending the EHT by adding a telescope in space. So again, don't have to go through this much in here, but basically the EHT has already been expanding over the last 5 years. And with this next generation EHT project and various other projects pursued around the world, there is a goal to really push it even further and add sites operating at multiple frequencies simultaneously, 230, 345, and 86, all around the world to really sort of fill in this Fourier plane of signals which we observe and get higher and higher quality images. And in particular, by adding more and more sites, we increase the number of measurements we have, the number of baselines or pairs of sites by n squared. And adding these really allows us to fill in information in particular about the very low brightness structure, which we think should be lurking just outside this central ring and should be really tracing the origin of the jet in M87 at 230 gigahertz. And I think this is exciting because this is a project I've been working on with grad student Zach Gellis at Princeton, who used to be an undergrad here. And he's been sort of extending the arguments which we just went through about the polarization structure on near horizon scales to larger scales by looking at jet models. And so, yeah, everything we talked about in the previous section was just looking at simple equatorial emission models. And he's really gone to much more complicated models, looking at different jet shapes, different jet acceleration profiles. And what he sees is that even when you fold in all these complications, and there's a lot of different classes and complications to worry about, but overall you do see a similar trend of sort of this average polarization angle beta 2 defined in an appropriate way with the distance along the jet caused by field lines winding up more rapidly in higher spinning black holes. And you can connect in the jet models this sort of rough transition region with the light cylinder of the jet, sort of this point at which the field is mostly spun up, or the energy is transitioning mostly from electromagnetic to kinetic. And sort of this overall strong signature of spin at the light cylinder in these jet models, I think, gives us hope that by maybe zooming out and looking at the jet on larger scales and tracking this evolution of this beta 2 parameter as a function of radius, instead of just looking at the one value, which we're looking at now with the HT, we might be able to make stronger statements about spin. And for NGHT, we've just done a very simple initial pass comparison, but what we showed is that by looking at some of our best current simulations of these jets, which I should have put here, were done by Yusuneto, who just left here. We were actually able to observe this swing in polarization with the NGHT. So the NGHT measurements over a whole campaign are here in red, and are here in the error bars, and the sort of intrinsic variability in the simulations is here in the bands. And we're actually able to distinguish at these sort of larger radii, sort of 500 microarc seconds away from the black hole, between these two different spinning simulations. So this is M87. Yeah, so these are simulations of the jet in M87, sort of further away, further downstream. Again, I think this is at 86 gigahertz, but with really high sensitivity from the NGAHT needed to capture the polarization structure as it's evolving over these scales. And yeah, so we're able to just, in this initial first pass comparison, show that you can distinguish between these spin 0.9 and spin 0.5 models just by looking at how the polarization changes as a function of radius, and changes more rapidly in spin 0.9 and goes closer to 0 with this metric.
Are the deviations at large distances due to systematic elements, or just?
Oh, these sorts of deviations?
Yeah, because it deviates from the mean.
No, yeah, absolutely. That's a really good point. So yes, as you get further and further away, the jet gets dimmer and dimmer. And we're sort of bumping up here at sort of the limit to where this sort of projected NGHT could start to constrain the spin. So if we were to go further off the plot, I would say we wouldn't detect the polarization.
It's interesting that they actually deviate on different sides when we have spin.
Oh yeah, that is interesting. I mean, I think you also see that the spin 0.5 is deviating more, and that's because the spin 0.5 jet is dimmer overall, because it has less power. Yep. Okay, so lastly, I will also again talk about something which is probably familiar to most of you, which is the Black Hole Explorer, which is a project led out of CFA, but which I am involved in as one of the jet science leads to effectively take a site from the EHT network and put it into space and sort of increase our resolution by a factor of 3 by connecting our ground-based VLBI network to this orbiting telescope in a mid-Earth orbit. And it'll achieve this by downlinking its data by a high-speed laser downlink connection to the Earth in real time as it's doing its observations. And sort of the key science goal of BEX is to discover and measure a black hole photon ring. And so this is the very narrow feature in these black hole images, which you may have seen throughout the talk and in many other images of black holes that you've seen in other talks. This is caused by rays that are bent around the black hole more than 180 degrees. And it's not something we can pick out of the image directly now. It's just our ground-based observations, which give us this sort of blurry donut. But by increasing our resolution by a factor of 3, we hope to directly observe this photon ring, which is a prediction of sort of GR lensing in sort of the most extreme limit, but also encodes a lot of information about spin and the mass of the black hole, which we hope to directly measure from the geometry that is producing this photon ring. So that's like one of the key science goals of BECS. It's also targeting sort of extending to the sort of EHT scale measurements to 10 different black holes and looking at a bunch of different jets at different scales. All that is very important, but I'm going to talk about something different, which is not part of the BECS official science case, but I think is something I've been thinking about more lately, which is trying to understand if BECS could probe the sort of universal value of the polarization angle which we observe at the horizon. So it turns out in sort of these axisymmetric GRMHD models, the synchrotron emission has a value of this arg-beta 2 parameter, or equivalently a value of the polarization angle on the horizon, which is determined only by the spin and inclination of the black hole. It's not dependent at all on any of the different choices you make about the magnetic field or the velocity of the plasma. And this sort of came out of these models, and we were really surprised by it and didn't understand it for a really long time. And you just sort of see that here. These are different equatorial emission models where the different bands here are showing a range of this arg-beta 2 parameter encoding the polarization structure as a function of image radius. And the bands are showing sort of a range of different models covering different magnetic field structure, different rotation rate of the fields, et cetera. And so you can see that there's like separation. You know, as we talked about already, the fields are wound up more quickly in the highly spinning case, the purple ones here, versus the low spinning case. But if you go zoom in this function of beta 2 as a function of radius, you see that at the horizon itself, they all sort of converge to a universal value. You can see that better zoomed in here. So of course, this point here is directly on the event horizon, so it's not something you could directly observe because it's infinitely redshifted. But it seems like in sort of the asymptotic limit, as you approach this horizon position on the image plane, all of the polarization structure sort of loses its dependence on the magnetic field, and you arrive at a universal value. And so something we first noticed in models, and now we've actually been able to sort of prove it directly. And this was first actually done by a paper by He Huo, and now we're sort of extending that past the equatorial plane in a paper in prep, which hopefully will come out soon. And basically, you can show that you get a universal value of the entire polarization pattern on the horizon. Again, this is something you wouldn't directly observe because it's infinitely redshifted, but in the asymptotic limit, it's something which you can describe entirely by just a few lines. You don't need to understand what those lines are. I just wrote them down because there are just a few of them to show that you could do it. And this image sort of shows what this polarization pattern looks like, where the color is showing the EVPA, the direction of the polarization, and the lines are showing sort of integrals along those EVPA, sort of what the ticks in the polarization would be, as a function of the inclination of the black hole at a very high value of black hole spin. And this is something which was actually shown in the high spin limit by a paper by Delilah Gates several years ago, but we've now extended it to all values of black hole spin. And in the equatorial emission case, all these complicated equations reduce to this simple value of arg-beta 2 at the horizon if you think you're viewing equatorial emission face on. And so we actually observe that sort of trend in equatorial emission models like this one, again, where we have a model for what the emission looks like, and here we're observing it face on, and we're making a lot of assumptions, that we're directly looking face on, but we see this overall sharp increase in the polarization toward radial values, or actually reversing the direction of the polarization helix by crossing the zero line as you get closer and closer to the horizon, and arriving finally at this universal value, which is only a function of inclination and spin. And sort of this rapid evolution, sort of interior to the black hole shadow radius, we think is being driven strongly by both the windup of magnetic fields in curved spacetime, which sort of has an opposite sense that you would expect, because you would expect the windup to only proceed in one direction. But actually, if you just look in the equations for the field sort of as observed by a distant observer close to the black hole, they have this opposite sense, and the parallel transport of light on its way from the black hole to us. And I think what's exciting is that this is a very, very idealized and not something you should take too seriously, but just an idealized reconstruction with the Black Hole Explorer, again, of this idealized model, the resolution and sensitivity we think we can obtain with the Black Hole Explorer plus the EHT on the Earth should actually give us the ability to potentially start to look at the behavior of this polarization interior to the shadow in this region where we're losing a lot of brightness rapidly, but the field is winding up in sort of the opposite sense, close to the black hole. And if we were actually able to observe this trend and connect it directly to models of the Blandford-Znajek jet launching mechanism, I think we'd be able to actually start to say whether or not we're actually seeing field lines which are taking energy out of the black hole, which are penetrating the ergosphere and approaching the horizon in this way, which is actually, at least in axisymmetric models, something that has a really precise prediction on as you approach the shadow itself, or the horizon itself. Okay, so yeah, I think both these directions give us a lot of hope for the direction of this field in the next 5 to 10 years. I think there's a lot we can learn both by zooming out with the expanded EHT or NGHT and by zooming in with high resolution by going to space. I think we'll learn both about the extended jet on larger scales and hopefully on what's going on in energy extraction on very small scales. Polarization is the key to all of this. My takeaways are here. I also think about these things. And yeah, happy to answer any questions. Thank you.
We have time for questions?
It's okay, I can shout. So you were focusing on the astrophysics, assuming GR. Can you say something about any constraints on general relativity that can be astrophysics independent?
Yeah, so I think the photon ring type measurements have the potential to do constraints on GR. I think just by looking at this n equals 1, I think we don't necessarily get enough information because we'll be primarily measuring spin. But if we were to, if in future satellite missions get higher and higher resolution and look at higher and higher order of these lensed rings, we could then start to make very, very precise tests of GR because GR has very strong predictions of how they relate to each other. I think it's a very interesting question on the polarization side about whether non-GR theories have different values of this asymptotic horizon value. I don't actually know the answer off the top of my head, but that I think would be a really interesting thing to look at. Yeah.
So in the last few slides, you're talking about inclination. Is that the inclination of our line of sight with respect to the black hole spin?
Yeah, that's right.
And so are people starting to do simulations where maybe the disk is inclined with respect to the black hole spin? What that would make?
Yeah, no, that is a very good question. And yes,
because you have retrograde and you have prograde, so there might be some states in between.
Yeah, absolutely. Yes, I completely glossed over that here, but yes, here we're just saying that the black hole spin is on like one axis where you have everything is aligned with the sense, the disk at large radii is aligned with the sense of rotation of the black hole, either aligned or anti-aligned. But of course, yeah, it is most likely not either of those. It's probably some intermediate state. Yeah, I would say many people do simulations of inclined accretion disks, but it's not been pursued as systematically, so we don't have these enormous libraries that densely cover different spin, and the simulations are more complicated and more challenging. So yeah, I'm hopeful that over the next few years we could maybe sort of start to add an axis to this plot. Yeah, yeah, so it becomes a larger parameter space, and yeah, absolutely, yeah.
Any more questions? Okay.
So the last part, Andrew, where you showed that this beta 2 flips sign as you come towards the horizon.
Yeah.
This is for an equatorial emitting region, right?
That's right, yes.
So what's the intuition? Why would it switch sign? Are the field lines bending over, or what is going on?
I have sort of struggled with this, and so yes, if there are any very relativity-minded people in the audience who want to help build intuition here, that would be great. I think if you just look at what we would call the magnetic field, so I don't know if I have this on a slide here, let me see. But if you look at like what we call the magnetic field in GRMHD, then the B phi over BR actually is changing sign as you go in, because B phi is blowing up as the field is getting more toroidal as you go in Fourier-Lindquist coordinates at least, because b phi is blowing up as 1 over delta. But that's a coordinate-dependent statement, so you shouldn't take it too seriously. Yeah, I don't have like a physical intuition for why this is happening, and I would really like to develop that. And I'm sure there must be one, but despite staring at the equations for a long time, I have not.
Is that this will happen regardless of whether you're prograde or retrograde, right?
Yes, absolutely, yeah.
This is something space-time dependent.
Yeah, that's right.
Nothing to do with accretion conditions.
Yes, because everything, if you assume you're equatorial and you assume you're actually symmetric, everything needs to arrive at this value by the time it gets to the horizon. And so, yeah, if it's down here at large distances, it's got to go over the 0 line at some point. And so, yeah, I think we can never observe this value directly because it's infinitely redshifted, but I do think, as I was trying to show here, that this sort of overall flip is something we could observe, and yeah, hopefully we understand it better and really understand the physics that's driving it, but I do think it's something to do with sort of the weirdness of how magnetic fields behave in the ergo region and parallel transport. But yeah, we'd like to make that more precise.
I actually have a follow-up question. So is this for using the inclination angle for M87?
No, so this is based on.
This is based on.
Yes. So yes, this exact value being one single thing in beta 2 is something you can only do for face-on. As you tilt away, you sort of diverge from that because basically, when you're exactly face-on, the field is rotating exactly as the polar angle. It goes to some value plus phi, and it rotates exactly like that. As you go to a little tilt it, you get some distortion, so it's pretty close to that. But yeah, we could definitely extend it.
Any other questions? If not, let's thank our speaker again. Oh, and there are some spots for dinner, so please sign up for the dinner.